Hello everybody, welcome to another video lesson. Today we're looking at functions and representing them as infinite series. After this video, we'll be able to use power series to represent a rational function and an exponential function. So let's hop into it. We're going to need to recall some information from previous chapters. So try to remember all the information that we've learned in Precalculus so far. But right now, just recalling 10.3 and representing the sum of an infinite series. The sum of an infinite series, remember, we called 1 plus r squared plus r to the third plus ... plus r sub n, and it really just kept on going, right? Plus even more, right? R raised to whatever power, r raised to the infinity power, where a sub 1 is equal to 1. Now remember, this converges to the expression a sub 1 divided by 1 minus r if the absolute value of r is less than 1. So we're going to go ahead and replace r with x now, because a lot of times when we think of functions, our input is x, right? Or our domain is x. So let's go ahead and represent this as the sum from n equals 0 to infinity of x raised to the n. So now, see, instead of having 1 plus r squared, I get 1 plus x squared plus x cubed, and so on and so on. And so this is going to converge to the expression 1 over 1 minus x instead of 1 minus r. If x now, again, x instead of r, if x, the absolute value of x, is less than 1. Now, let's go ahead and take a look at this graphically, how these kind of pair up. So if I were to graph the expression or the equation y equals 1 over 1 minus x, that's what I have here in red. And I'm also going to graph our second sum here. Okay, so the second sum is just these first two terms, so 1 plus x. Okay, so this is just the second partial sum of this series, represented as a function. So see how we have it, we are converging at this kind of just one point, right? Now what happens if I take a look at the third partial sum? Okay, so now I've got 1 plus x squared. So that's what's in blue here. So see how we have a little bit more overlap. Now I'm going to go ahead and take a look at the fourth partial sum. So 1 plus x squared plus x cubed. See, we have even more overlap. And even more overlap with the fifth partial sum. So notice that as n increases, as the number of terms in my series increases, we actually have more overlap and more convergence on my series when I compare that to my actual function. Okay, so we have more overlap, and our series is a better representation of that function with the more n terms that I have. Okay, so our power series we are going to represent as the sum from n is equal to 0 to infinity of a sub n x raised to the n. All right, and that just looks like this, kind of expanded generically. And we're also taking a look at exponential series. So recalling all the way back from chapter 3, our Euler number. Euler's number, E, remember how we say Euler here? E is defined as the limit as n approaches infinity of 1 plus 1 over n raised to the n power. Now we said then that e to the x was defined as the limit as x approaches infinity of 1 plus 1 over n raised to the nx. Okay, that's the only difference there when I look at e to the x. So with that information recalled, let's look at our binomial theorem and our power series representations and come up with a generic formula to represent these exponential series. So we're going to first start off with some u substitution and just some substitution in general. So I've got 1 over n, and I'm going to set that equal to u. And now I've got xn, and I'm going to set that equal to k. So when I do that, this term right here becomes 1 plus u to the k. Now this looks like the binomial theorem expansions that we worked on last lesson. So if I were to expand this, I would have k choose 0, 1 to the k, u to the 0, plus k choose 1, 1 to the k minus 1, u to the 1, plus k choose 2, 1 to the k minus 2, u squared. And we're just going to keep on going with that, right? So if I were to expand out these combination terms here, these combination coefficients, I'd have k factorial over k minus 0 factorial, 0 factorial, and k factorial over k minus 1 factorial, 1 factorial, and k factorial over k minus 2 factorial, 2 factorial. And notice that my u term is also gaining 1 as far as its index as well with each additional term. So I'm going to write this k factorial in a way that allows me to cancel out this k minus 1, k minus 2 factorial on the bottom. So I'm going to say k factorial is going to be equal to k times k minus 1 factorial. And k factorial here is going to be k times k minus 1 times k minus 2 factorial. And that's going to allow me to cancel out the k factorials in my denominators. So when I do that, we're starting to see we're simplifying here a bit. And now I'm going to go ahead and substitute back in my u and my k terms. Okay, so the limit as n approaches infinity is now going to be represented as 1 plus nx times 1 over n. Okay, I'm just substituting in u and k again into these terms. So instead of k, I've got nx, and instead of u here, I've got 1 over n. Plus, instead of k times k minus 1, I'm going to have nx times nx minus 1 over 2 factorial, and then instead of u squared, I'll have 1 over n squared. Okay, and so that's how that's what I'm doing here. I'm just putting back in these n terms instead of u's and k's. Now from here, I did some factoring. So for each of these terms, I factored out an n from each of these factors here. And so when I did that, I'm left with, instead of 1s and 2s, so I would be left with x minus 1 over n, and for this one it'd be x minus 2 over n, okay, because I'm factoring out an n, but this doesn't have an n term here, so it would be like 2 divided by n when I factor that n out. So when I do that, I'm left with this term right here, my 1 over n squared or cubed or whatever, that actually cancels out, and I'm left with just x's and n's in my numerator only. Okay, bring it back up. This was what we had at the bottom of the last slide. Now remember, this is in the context of the limit as n approaches infinity. Therefore, all of these terms with n in my denominator are actually going to approach 0. So this is going to approach 0, this will approach 0, this will approach 0. So now I'm just left with x terms being multiplied in my numerators. So when I simplify this, I'll have 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Now, if I take a look at this graphically again, I'm just going to take a look at 2 graphs here, but we'll see if I take the third partial sum, so 1 plus x squared over 2 factorial, and I graph that on the same coordinate plane as e to the x, see, I do have some overlap here, which is great. Now, if I were to take the 6th partial sum, I had to zoom out here, but see how much more overlap I actually have when I overlap that with, or when I graph that on the same plane as y equals e to the x. So same thing with my power series. As my n increases, right, so the more terms I have for my partial sum, the better approximation and the larger interval that I have where these two converge on each other. So now taking a look at an exponential series and just representing e to the x in a different way. E to the x we can represent as the sum from n equals 0 to infinity of x to the n over n factorial. That's exactly what we did up here, just writing this out in a little bit nicer of a way. Again, the more terms that I have in this series, the better representation I have of e to the x. All right, getting into our examples here, we're going to use our power series to find a power series representation of g of x, which is going to be equal to 1 over 1 minus 2x now, and indicate the interval on which the series converges. Then we want to graph g of x and the 6th partial sum of its power series. So first thing we want to do here, I want to set g of x equal to f of u. So we're going to use some substitution here again. So g of x is going to be 1 over 1 minus 2x. F of u is just going to be 1 over 1 minus u. So if I set these equal to each other and just solve for u, I would have 1 minus u is equal to 1 minus 2x, and that's going to give me u is equal to 2x. So g of x now is actually equal to f of 2x. And f of 2x I can represent as a power series as the sum from n is equal to 0 to infinity of 2x raised to the n. For now, instead of the absolute value of x being less than 0 or less than 1, we have the absolute value of 2x being less than 1. Okay, so this is now how we can tell our convergence here, because our series converges here of absolute value of 2x is less than 1, which is the same thing as -1 is less than 2x is less than 1. So if I were to divide everything in this expression by 2, I get the interval -1/2 is less than x is less than 1/2. So really I've done the first part of this problem already, where I found that g of x is equal to the sum from n is equal to 0 to infinity of 2x raised to the n, for x is in between -1/2 and 1/2. Now we need to find the sixth partial sum here, sixth partial sum of its power series. So I'm going to say the sixth partial sum of x is equal to the sum from n equals 0 to 5. Now notice here that my terminal point is 1 less than whatever number of my partial sum is. Because I have n equals 0 now, I want to stop at 5. I'm not stopping at 6, I'm stopping at 5. All right, of 2x raised to the n, that's going to be equal to, when I expand this out, 1 plus 2x. So here, n was equal to 0, so that gives me 1. 2x to the 1 power, that gives me 2x. 2x squared plus 2x cubed plus 2x to the 4th plus 2x to the 5th. So this is really what we're looking at with this sixth partial sum. And I'm just going to simplify this a little bit. So I've got 1 plus 2x plus 4x squared plus 8x cubed plus 16x to the 4th plus 32x to the 5th. Okay, so if this is what we're working with, then we want to graph the sixth sum of x along with g of x. All right, and g of x again being this right here. So I'm going to plug that into my calculator, and I'm going to plug this into my calculator. All right, so those are the two things, and I'm going to graph those on the same plane. And if I have a standard window, notice I get something that looks like this. Now, this is kind of difficult to see what's going on here. So knowing that we are converging on this interval right here, I'm going to then set that interval as my window. Okay, so my x values are going to go from -1/2 to +1/2, and we'll get a much better view of where we are converging here. Okay, so when you're asked to graph your function with the partial sum, make sure you are taking into account what the interval they are converging on and set that as your window domain. Okay, so you can get a very good idea of really what's going on. All right, second example here, looking at exponential functions. Use the fifth partial sum of the exponential series to approximate e to the -0.75. So remember, we can represent e to the x as 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. And so really all we're doing here is plugging in -0.75 for x. So when I do that, I get an expression that looks like this, and you don't need to simplify anymore at this point. Just go ahead and plug this into your calculator, and that's going to hopefully avoid any mistakes. So I would plug it in just like I wrote it out, right into my calculator, and you'll see that I get an approximation of 0.474. Now, just a little note here, in order to get this factorial sign in your calculator, if you've never done that before, so what I'm using down here in all of these denominators, if you hit math, which is the button under the green alpha button on a TI-84, and you scroll over to prob for probability, come down to choice number 4, and you see your factorial symbol right there. Okay, so that's how you can put factorials in all of your denominators. Now, we want to go ahead and check this. We have our approximation here of e to the -0.75 right here of approximately 0.474. Now, check this with your calculator by just plugging this straight in. Plug this straight into your calculator and see what you get. Now, my calculator got 0.472367 and a bunch more decimals. Now, if this wasn't even close to what we got over here for our answer, then I know I did something wrong. However, these are really, really close to each other, so we know that we have a good approximation here and we didn't make any mistakes. All right, guys, that is it for this video. Good luck with your practice.